Hello everyone. Today, inshallah, we will explore an application, one of the important applications on the diagonalization in general and on eigenvalues and eigenvector. This application is really very good and it summarizes or sum up all the process that we went through in the previous sessions. So it's really very nice. Okay. Of course, you know all our course notes, references, everything you will find on Moodle. Also, the recorded sessions for this campus, for this academic year, you will find them all on my YouTube channel. So enjoy. Okay, what I want to talk with you today is the dynamical systems. And we mean by dynamical systems is the systems that changing over time. So what we are going to do is to see one of the applications which run on a certain problem. We will try to find a suitable mathematical model for it, and then we will try to explore how to solve it. Okay, as I told you, it's a direct application on eigenvalue and eigenvectors and on the diagonalization process. Let's study this model in specific, which, as you can see, it's a study about the case of how the city population may change over time. So usually people move from place to another. Okay, so mainly the idea is once you live with a huge town, crowded streets, buildings all over you, you start about thinking of moving from this crowded place into another place where the air is fresh. There is the pressure of being in a crowded streets and so on. It's gonna be relieved actually. So we will study this population movement. Let's consider a population of a certain city of 30,000 and it's suburban with a population of 10,000. So you have two options living in a place with 30,000 people living over there, exhausting, breathing, eating, and so on, blah, blah, blah. And compared to another suburban place, which is much easier than that. It's just only 10,000, streets are empty, everything is available. So this is what we are going to describe. So for the time being, this is the city that we are talking about. And as you can see, by the time people will realize that living in this place, it's very stressful. So some of them will take the advantage of movement from cities into suburbs. According to this model, you will have first 5% of the people who are living in this town, they will be moved to suburbs. And that means that you will that 95% of the remaining population will remain in the city. So some of them will think if we went out, so it will start like 5% they will move, 95% they will remain. On vice versa, from suburbans, the percentage of people who need to go to the city in order to work, in order to do stuff, they will move over there if they got job opportunities or they are willing for getting more money or more chances. So 3% from them moved from the suburbans back into the city or into the city, whatever, leaving 97% of the people who are living in suburbans just staying over there. So now if you think about that clearly, you will find this model is proposing a problem for you. The summarization is that you have two places, one of them 95% will remain in it, and there is also 3% will be added to this population. For the other side, the suburbans will have 97% from their population will stay over there, plus a 5% that will be moved from the city into the suburbs. This problem, as described, can be easily put into a mathematical model to explain all of this. In order to start with the symbols that we are going to use in our mathematical model, let's introduce first the vector x sub t. So we will consider x sub t, which contains two components as we have two places, x1 of t and x2 of t, where t is the time of the movement connecting the cities into the suburbans, and x1t stands for the population of the city, while x2t stands for the population of the suburbans. So once more, in order to start our problem, you will have to choose the suitable variables that you will deal with through this model. So we thought that we will take x1t for the population of the city and x2t stand for the population of the suburbans at certain time. And as you can see, x1t is the population of the city and x2 is the population of the suburbans. The population movement can be described by. So this circulation of the population can be put in this form, standing for x1 t plus 1. So this is going to be the case the next year if we suppose that we are at the current year. So within the next year we will have x1 at t plus 1, which actually it is the population at t plus 1 at the next year, but this is the city population. And for x2, of course, you will have the suburban and also for the next or coming year. Okay, the next year you will have the following. You have 95% of the people or the population or living in town, they are the same, and you have 3% that's moving from the suburbans into the city. So once more, how we formulated this equation, it's really very simple. I am talking about the population of the city. Next year, how it's going to be formed. 95% of the people or the population will remain over there, plus there is a 3% that will move from suburbans, as we explained in the previous lecture. I'm sorry, in the previous slide. For x2, I'm talking about now the equation controlling the population number in the suburbans. So for the next year, you will have 97% of the people living in suburbans will be the same, plus the extra 5% who moves from city into suburbans. So this is how we can formulate the second equation. Now I've succeeded in transforming the problem into a math word problem into a mathematical model. And also we can, instead of dealing with these two equations, if we like, we can put them in a matrix form as we learned previously. So I can simply, instead of having x1 t plus 1 and x2, it's going to be the column of the values of the next year, which equal to a matrix that sums up the numbers already developed with the matrix. The first row explains what's going to be the situation next year in city, and for the second row, which explains how it's going to be within the next year for the suburbans. So multiplying this matrix, which controlling the movement, by the number of populations who already exist at this year, we can speculate the case on the next year. So actually, it can be summarized into xt plus 1 equal a times x of t. Okay, wait. This is remember me by something which is like a linear transform. Moving stuff from a place into another place. Using a matrix in the middle, controlling this movement, and so you are moving stuff from xt using the A matrix times the other column. Okay, what I want also to focus on before leaving this slide is how this movement or this matrix is formed. If you remark that the element 1, 1, which is 0.95, explains here actually the amount of population within the city. So I'm talking about the city within the first row. This is how it's gonna be fed. The first, you will have feeding from A to A, which about 95%. And for the second, you will have the extra movement from B into A. So adding them up, you will end up having the amount that's required for the city within the first. The second two numbers, which also show the case of the movement vice versa. Okay? So it's explaining the numbers controlling the town or the suburbs. How are you doing, Rob?
Alhamdulillah.
Alhamdulillah. I will give you a brief. I have to start, but I will give you a brief. Yes. Okay. The problem is we are trying to take something as a direct application on what we studied on diagonalization, on the importance of diagonalization, or the eigenvalue and the eigenvector. Okay. This model, I will review it with you shortly. Very short idea about it. Okay. In order for you to be easier on you to come to follow up, okay? I was telling everybody that we have a situation here for a population movement. It's actually like what we are at the time being, okay? So you have a city which is packed full with people, very crowded, and you have suburbans. So we will discover that, or for this problem description, simply, we have 95% of the population who are living in the city will stay in cities. And you will have 5% just thinking about moving from the city into the suburbs, which is gonna their life will be easier and everything will be easier for them. Okay? Yep. No, it's just an example. Maybe accurate or maybe not. Yeah, we are not really sure about this. Okay, but it's a model in anyhow. If you change numbers to the accurate numbers or a sample taken from an actual word in a specific place, of course numbers will be different. But it's a situation, okay? So for the population in the suburbs, 3% of them will move back into the city and 97% from them will remain in their places, okay? This is the situation that we are dealing with. We will go for a mathematical modeling for this problem. How to put it in a mathematical form. Okay, I will choose first xt, which stands for the population numbers in both the city and the suburbs. Okay. I will take 1 for the city, 2 for the suburbs. Okay, already explained. So x1 is x1 of t. It's supposed to be the population at the city at certain time t, and for x2, as I told you, it is for the suburbs. So if we try to control this movement of between these variables, we will consider the population situation within the next year, with taking in account all the details of this movement. Okay, so x1 t plus 1 stand for the next year, or once it is updated, and it will equal to 0.95% of the student of the population will remain in the city. Plus, there is a feed from the suburbans, which is 3%. As you can see, we have 95% will remain in their place, and there is a 3% will be added because they are moving from the suburbans back into the city.
Isn't that layout of input-output?
No. It's somewhat near to. It's a mathematical modeling, so it will be near to them, okay? Also, for x2, it's gonna be the same, but in this case, it is for the suburbans. So, mainly 0.05 stand for the direct feed from the city into the suburbans, and the 97%, it's the movement from the people who will remain in the suburbans. So, this can be easily put. Before you come, I was talking about this. This can be summarized in a very nice and short form of matrices. The first column, which explains how the situation be in the next year, This is the transformation matrix, which is responsible about moving the stuff from t into t plus 1. And this is the time being population in both city and suburban. Okay, which can be also put in this form. If you remark this form, it's a linear transformation form. Do you remember? It's a linear transformation form. Okay, but I also want you to put in mind to look at this situation. I have A and B. The matrix describes the movements from A to A. So the first row is talking about A, the second row about talking about B. So if I change it, the situation or the scenario of this problem into another application that, as we will see down the road, I want you to keep in mind that the first row stands for the first part of your problem, and the second row stands for the second part of your problem. So my problem here, the first part was the city, the second was the suburbans. So the first row, it's the feeding of the city, and the second for the suburbans. Also, remember that A and A, it's the people who are going to stay in their places. B to A, this is the feed for A, which is coming from B, and vice versa for the second row. Okay, perfect. Let's go for this. All what we described previously in the previous slide, it's described here, but in a short written way. So, stating that when a mathematical model follows the equation, xt plus 1 equal A times xt. Now you know what's xt plus 1, what's A, what's xt. Okay, where A is an n by n matrix, xt and xt plus 1 are vectors of Rn. Depend on the situation that you are talking about or you want to model. T an integer, which stands for the time, and this is what's called a dynamical system. Let us show how it is working. The mathematical model is given by this equation, and let's say how can you use it or get benefit from it in order to understand how the movement's gonna be in terms of numbers. So Rami, let's consider that the city population at the time being, or at 0 time, since when we start to run our model, 30,000.
Okay.
Where the suburbans are 10,000. What's gonna be the case within the next year? So the next year, simply, in order to evaluate what we are talking about, this is the population of the city, and this number is the population of the suburbs.
Okay.
So all I have to do is to just insert the numbers 30,000, 10,000 in replacement of the situation of x1t, x2t, which is the current situation. Okay, I will do that. Replacing x1t, which is the number of the population of the city in this phase, and also multiplying x2 of t by 10,000. The result will be, if you make this with the first equation, you will end up having 28,800. And if you insert these two numbers in the second equation, you will get the population expectations for the next year, which is gonna be for the suburbans, 11,200. Same way, like, if I want to get to know these numbers, how it's gonna be within the second year, okay, simply, I will, instead of substituting by T0, I will start substituting by T1. So I will replace x1t with 28,800 and x2 of t with 11,200. Same way, like, I will take this number in its place, the second in the second place. And this will leave me with the following, that for the second year, the population in city will be decreased to 20,000, 27,600 something. And for the suburbans, it will increase to reach 12,000 whatever. Okay, we can go for this forever. But let's see what's gonna be the case if we use 20 years, 30 years, 50 years, how it's gonna be. Remark that each year is the input of the second year. So each values you get, you can pull them in back and they get the values, expected values for the coming year, and so on.
Okay.
So it's really very simple. Okay, let's forecast. Considering the same situation on the previous slides, assuming everything remained the same. Okay, so step by step, this is what's gonna happen. This chart explains the situation with this movement between these two cities, between the city and the suburbans, during the 20 years, 50 years, 60 years from now, and this is very, very important stuff. So if you remark that at 0 time, these are the numbers, 10,000 for suburbans, and 30,000 for the towns.
Okay.
The cities are decreasing with time, while the suburbans are increasing with time, and this is logic. Okay? Okay, they will start, the first, the movement in the cities are decreasing, and the suburbans are increasing, since you hit a single point, while they will intersect, and then, what's really matter, what's gonna happen down the road? Down the road, the numbers of the city will converge to certain population number and will be kept like that. And the suburbans, same way like, will also converge to a certain number with time, and it will remain like this.
On maximum population down there.
Maybe maximum population, maybe the chances for work or education will stabulate the same, will lead to a steady state case.
Okay.
Each one is happy in his place, okay?
But
Okay, yes?
to calculate exponentially, over 20 or 50 years, do I need to do?
Well, we are not, but we will study how it's gonna be depending on this model, okay?
Okay.
Okay, so all I have to do, if I want to go through what you have said, okay, it's ahead of the time, we will go through it, but we can explore this by taking a limit to infinity, for example, for this model, and see how it's gonna go. Okay, so we will go through this step by step for the time being. So, this is the movement as we spoke now. This is 95% in the city, 5% exactly the same. This is the equations controlling all of this. Okay, now I have a problem. My problem is, if I want to speculate the number of populations after 10, let's say 10 years from now, I will have to go one by one through this equation, and this is not gonna work. I need to know what's gonna be the situation after 100 years, after 200 years, what's gonna be? So I need to think about this point. This process can go for any time, building a table for us. So these equations can help you out to build the table for the points that represent the movement from the city and from the suburbs. Okay. Us each year will develop the next year, but what if we want to know in a specific at certain year what's gonna be the number? So we need to find some form or something that I can just rely on replacing the time and I will get the outcome. Okay, we will think about this. To do this, we can form a given system. We can go through this. AT plus 1 equal A times x of t.
Okay.
And this is mainly the matrix A, which summarizes the city and the suburbans that we want to go through, and I will explain this for the time being. This is our knowledge for the time being. Okay, let's remark something. This is mainly x1 t plus 1, x2 t plus 1. This is the A matrix, and that's the count that represents x node or the population in city at the time being. Okay, let's remember how we got the values for the first year. We got the values for the first year simply by replacing the values of x1 and x2 by the initial values, which were 30,000 and 10,000. Okay, if I want to get the second year, what's gonna be? Okay, I will replace this part by 28,800 and this one by 11,200. And I will get the new values. I want you to think just a little about these movements. I've replaced the 30,000 and 10,000 by this value. I've taken this value and then inserted it. And same way we'll go for the next year, okay? But I can replace these values instead of that form by these two forms. Yes? Okay, if I did so, it means that I am replacing this matrix by A times X. So it's going to come up to, if you remark, A times X, which is stand for A squared times X original.
Okay.
So after 3 years, I will have A to the power of 3 times X naught.
So
After 10 years, it's going to be this matrix multiplied in itself 10 times, okay, and so on. So now we can summarize that X naught equal A X naught, X1 equal A X naught. This is the replacement that I told you about. We ended up having A to the power of 2 times X naught. This is exactly what happened. If we generalized these steps, we will end up having this model. So now, if I want to know the situation after 50 years or so, all I have to do is just to come here, grab this T, replace it with 50, voila, you will have the time, you will have the simulation situation after 50 years. Now, this is mainly what we did, AX1, AX node. This is the X1 replaced by AX node, so it's going to be like this. So it has been done and proved that it's an exponential form, A equal to X to A to the power of T times X node. معايا رامي? Okay, perfect. If we want to know how the situation, we already talked about this. All I have to do is to just replace T by 50 and I will get the value. This is why, stop. This is why diagonalization, oh, dang. We went through this, but in a vast way. Rami, the previous numbers were easy. But remember that you are dealing with matrices. So A to the power of 2, it means you will multiply the A matrix, if you remember it, by itself 2 times. 3 stand for multiplying this value by 3, and so on. So it's not that easy in matrices, am I right?
Yeah.
But it will be easier if you remember how to diagonalize the A matrix. Because if you have a diagonal matrix, and it is power 2, just only the elements of the diagonal will take the power. Okay. So maybe I can change the A matrix into a diagonal matrix. And this is the head that we need. All the problems explained, all this problem explained before this slide or before this comment, we were talking about a certain problem, explaining the problem by itself, plotting the mathematical modeling. Now, from now, I will start getting advantage from the diagonalization process that I'm telling you about.
Okay, so
now,
I diagonalize the matrix D.
I'm going to generalize the matrix, diagonalize the matrix A by the eigenvalues and the eigenvectors, and the outcome, my life will be easy in evaluating at any time. Okay?
So
this is the main idea.
الdiagonalization هو اللي نطلع الايجن values صح؟
Yes, exactly right. Oh, remember how we do generalization in the previous lecture? Simply, I have A, it's gonna be, okay, factorized into B times D, that's the diagonal matrix that I'm telling you about, times P minus 1. My quest now is to find the matrix P in order to diagonalize A or to get the advantage of this process. Okay, really very simple. This is the matrix that we need to talk about, which is A to the power of T. So this is mainly the matrix that we will diagonalize. So I will start taking this matrix, getting the eigenvalues of it, then I will go through the process of eigenvectors, forming the matrix B. Since you have matrix B, so matrix D is really very simple because the diagonal matrix, okay, or this diagonal matrix will have the eigenvalues as the elements on the diagonal. So I'm winning. Okay, let's go through it. Here, if A is similar to a diagonal matrix, this is explaining exactly what we are talking about. All I have to do, A is similar to a diagonal matrix, blah, blah, blah. So if I have A to the power of K, so it's going to be B, dk, B minus 1. B is the targeted matrix that I will evaluate from the eigenvalues, as you know. This is, I want you to remember all of this. Also, there is some interesting remarks We did go through them in the previous lecture that may make your life easier in evaluating the values of eigenvalues or eigenvectors. Let's read them once more. One of them, or the first, stating that the sum of the eigenvalues will equal to a trace of the matrix. Do you know what's the trace of the matrix? The sum of the elements of the principal diagonal. This is what's called the trace. So, for a matrix, if you have eigenvalues, the eigenvalues sum will equal to the trace of this matrix. Okay, the product of the eigenvalues of A is equal to the determinant of A. And this is also a very nice remark. The geometric multiplicity of each eigenvalue is not larger than its algebraic. If each row, this is important, this is really important. If each row of A sums to a certain number, so if you have this matrix A, and you get the sum of the elements in each row, and it's summing up to a certain number, this number will be an eigenvalue, okay? And also, you will have an associated eigenvector to one of these eigenvalues which contains ones. So if you are in R2, for example, you will have 1 and 1. In R3, 1, 1, 1, and so on. Also, for the columns, if you collect the numbers for the columns, it will come up to a certain constant, but you are not going to have, we are not sure, it's not necessary to have the one vector already from your eigenvectors. Okay, man? Okay. Let's start all of this. The sum of eigenvectors, I'm just focusing on this remark and on that remark also. Let's now try to solve this problem. This is our problem, mainly. The problem that we were talking about the city, blah, 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 the movements and everything. I have the A matrix. The A matrix is, okay, just check that the board now is in the control of the camera, please. Okay. So the A matrix stands for the numbers 0.95, am I right?
Yeah.
0.03, 0.05, and 0.97. I will remark something. I'm taking into my mind the two remarks that I told you about in the previous slide. If you remark the sum of the elements for this matrix, this is matrix A, trying to get the eigenvalues and eigenvector for this one. So, if you remark that the sum of the elements for the first column will add up to
1,
and for the second also will also their sum equal to 1. And this will lead to the fact that one of the eigenvalues is positive 1. This is one of the lambdas of the eigenvalues.
Okay.
And also, I have the trace here with me. So if we get the trace of the A matrix, which is simply 0.95 plus 0.97, so I believe it's gonna come up to 1 point, let's use a calculator or something. I believe it's gonna be 1.92, am I right?
Yeah, 1.92.
Okay, perfect. So this is the trace of them. So since this matrix is a 2 by 2, now I have lambda 1 equal to positive 1. And I know that's equal to lambda 1 plus lambda 2. So simply lambda 2 will equal to 1.92 minus 1, which is gonna lead to that the second lambda equal to 0.92. This is really very interesting because the other way around, in order to get these eigenvalues, yes, you are right, Mr. Rami, what you said is right. I can use the characteristic equation, and that's the main step or the standard that I will use A minus lambda times I equal to 0, as you know. And this is gonna be on the form that's the determinant of this matrix, which is 0.95 minus lambda 0.03 0.05, 0.97 minus lambda equals 0. And this is what's called the characteristic equation. Do you remember? This is how we get the eigenvalues and eigenvectors without taking advantage from the two remarks that I've told you about. That the sum of the columns will give you one of the lambdas, and then the sum of the, or the trace of a matrix, it's equal to the sum of all lambdas. So this is the way around this standard method, or the standard equation. Okay?
Okay.
Now I'm ending up that I have lambda equal 1 and the lambda 2 equal 0.92. Corresponding to each one of these lambdas, I can get what? I can get an eigenvector. How to get an eigenvector in this situation? I will talk now about the first vector, which is u1. That corresponds to lambda 1, which equal to positive 1. Okay, Mr. Rami? Okay, how to evaluate this vector, Rami? All I have to do is to solve the system, if you remember, which is a homogeneous system that states that I have a 2 by 2 system of equations which have 0.95 minus lambda 1, which is 1, and 0.03. And for the second row, it will be 0.05. Then I will have 0.97 minus 1. This equal to 0, and that's equal to 0. Okay? So, trying to solve this system of equations for the coordinates of the first vector. For the coordinates of the first vector, Rami. All I have to do, 0.95 minus 1, you will end up having minus 0.05. And this is value 0.03. And the result equal to 0. For the second row, it starts with 0.05. And this value is going to be minus 0.03 and 0. And as we spoke previously,